Hello, everyone. Thank you for joining me on this presentation. Hopefully it will be either a bit of an introduction for some, as well as a bit of a refresher for others on some of the fundamental concepts surrounding measurement uncertainty, alongside some examples and some FAQs as well. Alrighty. So I guess many people tend to interpret lab results as being exact measurements that are potentially an absolute truth for a patient. Realistically, anytime anything is measured, there's inherent and unavoidable variation in the result. And so a single lab result should actually be taken to represent a range of possible values. And measurement uncertainty is just one way that we can use statistics, really, to express this range of results associated with a single measurement. Understanding and being aware of measurement uncertainty can, in some instances, help to prevent potential over or underinterpretation of data, and ultimately contributes to diagnostic accuracy and ultimately patient care, which is what we're all here for. So although we are introducing MU to align with regulatory body requirements as well, it does have a sound underlying justification, in my opinion. This is just a quick visual representation of what a single lab measurement reflects. So rather than thinking of it as an exact value, it's probably more accurate to consider it as a range of possible values. Now, how broad this range is depends on many factors, which I'll go into. But ultimately, I guess the question that we're always asking ourselves, and I'm sure is on everyone's mind, is why do I really care about this, and does this matter? Now, in order to explain the importance, or potentially in some instances, the lack of importance of measurement uncertainty, is to understand why values change. And this sounds slightly trivial, but recognizing and grouping different sources of variation can help us with understanding what measurement uncertainty does, and again, probably equally importantly, what it doesn't tell us about. So variation in a measurement can, of course, be due to a change in the disease or health status of an animal, a response to therapy or management, that sort of thing. And this is typically the reason why we're doing testing in the first place. And this is the a signal that we want to detect. So in order to read this signal, we need to consider how loud it is compared to what I like to think of as background noise. And so this background noise can be due to biologic variation. So in other words, normal biologic fluctuation around a homeostatic set point. It can be due to analytic variation. So this is variation associated with the actual measurement process itself and the test system. And this encompasses a ton of factors which can all influence the measurement. And these could be environmental, so believe it or not, the temperature, humidity, water quality, that sort of thing. Human factors, pipetting consistency, variation in quality of the reagents that we receive from manufacturer for a test, calibration, power supply, the list is really endless. But generally, modern testing methods and laboratory equipment means that this analytic variation is usually much less in comparison to biologic variation. And indeed, that's one of the factors to be considered when judging whether or not a lab test is acceptable for marketing and use for diagnostics. And finally, of course, it's important to remember that we only deal with the sample that we receive ourselves. So artifacts or potentially errors introduced as a result, let's say, of sample collection or transport or a really hot day or something like that, can also introduce variation into our results. So just to illustrate these sources of variation, I'm fairly visual person, so I've drawn a couple of stick figures for your entertainment and understanding, hopefully. So let's say this is me, and I have a bunch of different homeostatic set points for various analytes. So for example, cortisol concentration, it could be temperature, etc., etc. And in an ideal measurement world, there's only a change in this value because of disease or treatment or some change in management. So for example, I start taking corticosteroid medications, or I develop Cushing's or something like that, and that's why there's a change. But there are other changes which we can see, and that is with biologic variation. And this is due to the fact that we're not always exactly at our homeostatic set point. So many factors, for example, circadian rhythm, diet, stress levels, they can all affect my cortisol levels. And those levels will all be still normal for me, but they may vary hour to hour, day to day, month to month, etc. And so both with this short and long-term change, that introduces another source of variation, which isn't necessarily due to disease treatment management. And the main source that I want to illustrate for the purposes of measurement uncertainty is analytic variation. So this is attributable to the way that we measure the result itself. Even if I run the same sample through the machine multiple times, I don't expect to get this same value every time. And that's due to those unavoidable factors that I mentioned previously. And this analytic error is what is characterized by measurement uncertainty. So it's important to understand that biologic variation, or even pre or post analytic changes, is not reflected in measurement uncertainty. So we still can't blindly use lab results plus or minus measurement uncertainty to say, oh, there is disease or there isn't disease, that sort of thing. Because again, even if we've discounted analytic variation as a cause of the change, there are still other non-disease factors and sources of variation. And again, this slide just illustrating we only see the sample as received, so potentially pre and post analytic factors can result in variation. All right, back to words now, and probably a little bit of repetition, but again, I really just want to emphasize the fact that measurement of uncertainty only reflects analytic variability and analytic variability alone. So again, if there's a change in an analyte that potentially, let's say it's within the degree of measurement uncertainty, that potentially just could be due to the small amount of error in the machine and test rather than a change in the patient status. If there is a larger change, then that could be due to disease treatment. It could be due to biologic variation, but we can be more confident that it's not just due to results in our tests method. So we still need to ultimately interpret, I guess, in light of the actual patient, not just looking at the numbers themselves. In terms of how we actually calculate measurement of uncertainty and analytic variation, this is principally done through replication studies, essentially repeat testing of a sample or quality control material. And then finally, it's worth mentioning that our measurement of uncertainty is often based off a 95% confidence interval, but this can change depending on how important it is to distinguish small changes in a particular analyte. I guess getting into a couple of examples of what measurement uncertainty might look like to start off with, and then a few examples into how we can actually use measurement uncertainty. Measurement uncertainty can be expressed in many ways, both in relative, so basically percentage terms, or absolute values. So this first example here is in absolute values. So let's say for glucose, I've got a result of 4.5 millimoles per liter, plus or minus my measurement uncertainty of 0.2 millimoles per liter. You may also see it as an interval. So again, my measurement is my result is at the front, 4.5 millimoles per liter, and then the range of possible measurement uncertainty, that interval is reflected by these square brackets. So based off this single test result, we can be confident that the result in the sample is somewhere between 4.3 and 4.7. It can just be spelled out in words. The measurement uncertainty at a certain concentration is a certain percentage. And then I've just taken a few screenshots of measurement uncertainty reporting from different labs. So this is what you may see potentially in some of our reports. This is from another laboratory as well, where they also spell it out more sort of in the footnote. Okay, so I've already mentioned that analytic variation and therefore measurement uncertainty is often small in comparison to biologic variation or disease and treatment effects. And what that means is often the measurement of uncertainty is not relevant to the interpretation, because the degree of change is just obviously too far large, far too big to just be due to machine/test random error. But it does become more relevant when results are borderline or near reference range limits or critical and medical decision limits, for example, iris staging. So just to go through a couple of examples that I just pulled out very recently. So for example, in this was just a general wellness check for a middle-aged dog in-house. The platelets were a little bit low, but we can see at our lab result that they were fine, so probably just some platelet clumping, which is good. We did notice, however, on this profile that the hematocrit was, as you can see, just a little bit above the reference interval. So what I did is I went up and looked up the measurement of uncertainty for hematocrit. So that turned out to be about 3%. Based off that, I could work out and say, okay, well, this value of this hematocrit of 0.58 actually could represent a range of possible values between 0.56 and 0.6, and therefore, statistically, this result and this change above the reference interval could just be due to basically variation in the testing methodology, that sort of thing. And at this tiny amount of change, I can't tell if this is just a purely normal result within the reference interval or if there's a true mild tiny increase. But medically, we know that this probably isn't going to be too important. So I could potentially say, it could be due to analytic variation as we demonstrated. It could also be due to biologic variation, a slight change in hydration status, and then other factors can also contribute to this change. So potentially some in vitro cell swelling, and then maybe we are a little bit hemoconcentrated as a result of splenic contraction or something like that. Again, another example where hopefully it'll be a bit more obvious that the measurement of uncertainty isn't really going to be relevant to our interpretation of results. So this was an older cat, came in for a geriatric cat profile, did have some clinical signs of weight loss and PUPD. So just sort of eyeballing this glucose result up here, we can sort of already know that this degree of change is obviously going to be too far, just much too great to just be due to test or analytic variation itself, because we know that all our lab tests have been judged acceptable based off relatively low analytic variation. But just for completeness, I did go ahead and look up the measurement of uncertainty for glucose, sitting between 5 and 6%. Doing the maths, I can see, okay, potentially the range of results that could be associated with this glucose value, somewhere between 24 and 26.8. And we can see that that lower end, 24, is nowhere near the upper and nowhere near the reference interval still. So I can be very confident that this is not due to analytic variation and the true value in the sample is increased. But of course, the statistics don't really help me as much as the actual medical interpretation, taking into account the patient's signs, signalment. We can be fairly confident that this is probably going to be diabetes. On the same profile as well, maybe one that isn't as obvious is the total protein. So you're thinking, oh, it's a little bit above the reference interval, but is this just analytic variation? Again, I pulled out the numbers. Measurement of uncertainty for total protein, sitting at about 4.5%, and just doing the maths in this particular result of 91 could actually represent a range of values due to from 87 to 95, and I can see even this lower end of the range here is above our reference interval, so it gives me quite a good deal of confidence that the total protein in the sample is increased above the reference interval. And then the question is, clinically, why is that increased? And do we really care about it? And probably not. It could just be due to mild dehydration, especially if this cat has, polyuria. It could potentially just be due to biologic variation. And then, of course, we do know that looking at the total protein fraction, potentially it could be due to the high globulin. So maybe there's some chronic antigenic stimulation there. But ultimately, even though we've discounted analytic variation, we still don't necessarily say this is a really significant result. I'm not really necessarily jumping up and down about that total protein result. This slide, again, just visually to highlight that even though we've discounted analytic variation, so our result is outside of that measurement of uncertainty, I guess the result is outside plus or minus that measurement of uncertainty, it still is not necessarily just due to disease or treatment or management. We still have to take into account biologic variation and hopefully very minimal pre and post analytic sample artifacts. All right, so I've also got a couple of potential frequently asked questions that I've just made myself, but there is also a resource available online, which I'll share in a moment. It's more of a briefer fact sheet that also has some further frequently asked questions. I will just flip through these fairly quickly. If you wish to, you could obviously pause and have a bit more of a read. I guess I'll highlight a few questions. For example, the reason why we don't have measurement of uncertainty for all analytes. So it's only available for quantitative number tests within our working range. So that means you won't see measurement uncertainty for tests that are just positive, negative, presence, absence of disease, that sort of thing like that, or where the result is outside the working range of the analyte. So if the result in the sample is too low to be detected, then it's just too low. There's no point really telling you about the measurement uncertainty. Or if it's really, 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 really high, we can't actually calculate the measurement uncertainty there because we don't really have, these samples that we can constantly test and say, okay, this is what that measurement of uncertainty and analytic variation is for these really, really high results. And again, clinically, it probably doesn't really matter because we know it is really high and it's not going to be due to analytic variation and measurement of uncertainty. One thing I will highlight on this slide is the fact that measurement of uncertainty doesn't really at all relate to the concept of harmonization. So we still can't take, let's say, our result plus or minus measurement uncertainty and test it at a different lab and say, hey, why don't these two values necessarily align? Ultimately, the test methodology, the way that we test these analytes can differ between labs, between machines, and therefore you still need to use the lab-specific reference intervals to interpret results. And measurement of uncertainty doesn't really relate to that concept of harmonization. If you are potentially interested, I really believe that this first journal article in veterinary clinical pathology by a few of the experts in the field, Russell Moore and Kathy Freeman, really an absolutely excellent read. It is a brief journal article. Well, it's actually not too brief, but it is a journal article, and it does do an excellent job of explaining, I think with clarity, not only measurement uncertainty, but other closely related concepts. This is the link to our online available frequently asked questions. It should also be available. You should be able to navigate through our website, or even just a quick Google should show that one up. And then a few other resources which I've used for this presentation itself. All right, so thank you so much for joining me for this brief session on measurement uncertainty. I hope this helps clarify a few issues and gives at least a basic understanding of what it is, why we're introducing it, and how we can use it to, I guess, ultimately help improve patient care. Thank you so much.